Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqbal bin Fazil and my metric number is AA200988. Today I would like to present objective 1 for this project. So this is the first circuit. This is closed loop system without controller with unity feedback. So this is the circuit. So here is mathematical calculation. So GS 1 over S squared HS equal to 1. So we want to find TS. So this is a formula. TS equal to GS over 1 plus GS HS. So we just take this value and use this formula. So we get the answer 1 over S squared plus 1. So zeros and poles. Zero is a root for numerator and poles is a root for denominator. So this is numerator and this is denominator. So zeros for this circuit is 0 because this is the constant number 1 and it is 0 and the poles is I and negative I. This is get from imaginary solution. So we get this value. So after we get this value, we can sketch a graph. So this is the graph from the poles value. After that, we can prove it at MATLAB command. So we just follow the command and so this exact map. Grid on. Sorry. This is the pole zero map. So this here. This. So I1, negative 1i. 1i and negative 1i. So we get the same value calculation and MATLAB. So the conclusion for this circuit is the system is marginally stable. This is because both poles are on the imaginary axis. For the zeros, it is at S equal to 0, the x-axis and the y-axis. So we go to second circuit. This is closed loop system without controller with unity feedback. So this is the circuit. So the calculation is GS equal to 20 over S squared plus 2S plus 9. HS is equal to 1 and TS equal to GS over 1 plus GS HS. So we just take this value and add in this formula. So the zeros is 0 and the poles is negative 1 plus 5.29i and negative 1 minus 5.25i. So this is the graph, sketch graph, and then we prove it at MATLAB. So this, we use this command y tf 20 Sorry. Oh. So this is the pole zero map. This is the value. -1 plus 5.29i, -1, -5.29i. So it is the same value from the calculation and the MATLAB. So conclusion for this system is the system is stable. This is because both poles are at the left hand side, this and this. And for the zeros, it is a 0 as it is at s equal to 0, the x-axis and y-axis. We move to the third circuit. This is a closed loop system without controller with unity feedback too. And this is the circuit. So the calculation, GS equal to 250 over S squared plus 4S plus 50. And then after we calculate by using this formula, and we get the answer 250 over S squared plus 4S plus 300. And the zeros is 0. The poles is -2 plus 17.2i and -2, -17.2i. So we can prove it at MATLAB. So we just for that this pole and we get this graph, and then we can prove it by using MATLAB, and we just follow this. We just follow this command R equal to TF this 250 S sorry 1 4 3. So this exact map. This is R. Break on. So we get this graph. This is the graph. So we get two poles at the left hand side. This -2 plus 17.2i and -2 -17.2i. So this is the same value from the calculation. So conclusion for this system is the system is stable. This is because two poles. Both poles are at the left hand side, and for the 0, it is at s equal to 0, the x-axis and the y-axis. So we move to the last circuit. The last circuit is closed loop system without controller with feedback, and this is the system, the circuit, and the calculation is GS equal to 250 over S squared plus 4S plus 50, and HS is 2 over S plus 2. So we just use this formula and we get the answer is 250S plus 500 over S cubed plus 6S squared and plus 58S plus 600. So this is the answer. And the zeros is the zeros is S equal to -2, and the poles is -8.052, 1.029 plus 8.571i, 1.029 to 6 minus 8.571i. So from this three value, we get this graph, 2 poles here and 1 pole here, and we can prove it MATLAB. Okay, so we just follow this MATLAB command. So this v will tf 250 216 600. Okay, z map b grid 1. So there we see this is the value. This you have three values, so 8.0.05, negative 8.05, and 1.03 plus 5.57, 8.57i, and 1.03, negative 8.57i. So this, you get the same value, and this is the zeros, negative 2. Yes, we get negative 2. So the calculation and this same, this is. So conclusion for this circuit, the system is unstable. This is because two poles are at the right hand side and one pole is at the left hand side. Real number exists. For zeros, it is at s equal to negative 2 here. The x axis and the y axis. So that's all from me for objective 1. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nazmi Bituhid. My metric number is AA200972, and I will explain about our objective 2 project, which is simulate the closed loop system to obtain the step response. For circuit 1, you need to do this circuit first, and then you need to, from Simulink model, just click step, subtract, transform shading scope, and drag all them down here, and then connect them just like this. And then for step you need to change to 00110 and then click apply and then OK, and then you need to click run and then click on the scope, and you will get the graph here in Simulink. And to get step response from MATLAB command, you need to write this command first. G is equal to TF. This is for the numerator, and then this is for the denominator. And then type this one, and then T0 10, and then step TT. And then after you click this one, you will get the step response here, which is same with Simulink MATLAB. Okay. As for result, according to the pole zero plot, closed loop system 1 is an undamped system because the response oscillates with a constant amplitude. The closed loop system is marginally stable and will not settle down. As a result, there will be no settling time and infinite steady state error. So for this graph, there is no overshoot, rest time, settling time, and steady state. For circuit 2, I will show you example for circuit 2. For circuit 2, first we need to change the transfer function first into the numerator need to change to 20, the denominator need to turn to 1, 2 and 9, and then click apply and then OK, and then click run and then click on scope, and you will get the graph here, which is the same. You will get the step response from Simulink, and then for MATLAB. For MATLAB, you just need to G 0, 0, 20. Oh. 20. 1, 2. 9. And then T is equal to feedback G1. Oh, yep. And you need to write this command here, 0.01. And you will get the step response from MATLAB command. Okay, from here you can get the value here from right click on the step response and then pick response, settling time, rise time 60, and then left click, and from here you will get the value for peak amplitude, overshoot, time, rise time, settling time, and final value. So as a result, closed loop system 2 is an underdamped system because the amplitude of the motion is continuously decreasing with time as the system attempts to return to its initial equilibrium position. So for overshoot, you can get it from here. For rise time, you can get it from here. Just roll it down. Settling time, you can get it from here. And steady state error. Steady state error we can get from there. Okay, so for the next one, for circuit 3, same as step 2, you need to change the transfer function. The transfer function first, you need to change the numerator to 250, and then transfer function to 1, 4, and 50, just like here. And then, if you click run, and then click scope, you will get the graph. You will get the step response like this. And then if you want to get the step response from the MATLAB command, you need to do this command, which is same as before. Just change the numerator here and denominator here. Just copy, and then after you done this, you will get this one. And same with the step response from circuit 2. You just need to right click here and characteristic, and then it will come out just like circuit 2. So from here you will get the overshoot 69.3%, rise time 0.06%, settling time 1.87%, and steady state error 16.7%. So closed loop system 3 is an underdamped system because the amplitude of the motion is continuously decreasing with time as the system attempts to return to its initial equilibrium position. And for the last one, this circuit is different from the other because I have two transfer function here, but still. Okay, first you need to add another transfer function here, and then the numerator and denominator here no need to change. It is the same. For transfer function 2 here, you just need to put 2, 1, and 2, and then feedback. And for the circle for here, you need to add another transfer function, and then put another command here, which is 2, 1 and 2, and then feedback here, and then put this, and then click enter, and then you will get step response for MATLAB command here. And then for step response for Simulink, just need to, after you done this circuit, and then just click run, and then click on scope, and you will get this graph. So as a result, the closed loop system fault is unproven, unstable. Thus, it can be neither be determined as underdamped, overdamped, nor critically damped. So no overshoot, no rest time, no setting time, no steady state error. As a summary here, for closed loop system 1, it is marginally stable. For closed loop system 2, it is stable. And for closed loop system 3 is stable, and closed loop system 4 is unstable. The overshoot for closed loop system 2 is 55.2. For closed loop system 3 is 69.3. For settling time, for closed loop system 2 is 0.2 to 1. For closed loop system 3, 0.065. For rise time, for closed loop system 2 is 3.02. For closed loop system 3 is 1.87, and steady state error for closed loop system 2 is 31. And lastly, steady state error closed loop system 3 is 16.7. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Kifayatullah bin Kamis, number metric AA 2025. I want to present my part, that is Objective 3, Circuit 1 and Circuit 2. So I already stabilized the system using PID controller. So this is the result. This is result for Circuit 1. I have achieved the requirement of overshoot that must below 10% by GET 4.737%. I also achieved the requirement for settling time that must below 5 seconds by GET 2.588 seconds. The steady state error is 0% because the y-axis have reached 1, so the steady state error is 1 minus 1 times 100%. So next is Circuit 2. I also already stabilized the system using PID controller. So this is the result for Circuit 2. I already achieved the requirement of overshoot that must below 10% by GET 0.149%. Next, I also already achieved the requirement of settling time that must below 5 seconds by GET 4.292 seconds. Lastly, the steady state error is 0% because the y-axis have reached 1. So the steady state error is 1 minus 1 times 100% is equal to 0%. So I think that's all from me for my part. That is Objective 3, Circuit 1 and Circuit 2. Thank you.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irfan Bidan Syarif. My metric number is AA200960. And I want to present Objective 3, Circuit 3 and 4. I already stabilized system by using PID controller. So this is the result. First, we must run. And this is the result. I already achieved the requirement of overshoot that must be 10% by get 2.577%. I already achieved the requirement of settling time is below 5% by get 4.591 second. The steady state error is 0% because the y-axis have reached 1. So the steady state error is 1 minus 1 times 100% equal 0. So circuit 4, this is the result. This is the result of circuit 4. I already achieved the recommend of overshoot that is 10.4%. I already achieved the recommend of setting time is must be below 10% at 5 seconds by get 0. By get 2.39 seconds. The steady state error is 0% because the y-axis have reached 1, so the steady state error is 1 minus 1 times 100% equal 0. I think that's all from me. Did the circuit 3 and circuit